Imagine a single building consuming enough electricity to power an entire small city. And I'm not talking about some futuristic sci-fi colony on Mars or a villain's lair.
Yeah.
I'm talking about that unassuming concrete block down the road, the data center.
Yeah, it's a staggering reality that I think most people just don't see. We're looking at modern supercomputers and massive AI data centers specifically, drawing somewhere in the range of 20 to 30 megawatts of power.
Wow.
Right, and to put that into a context that actually hits home for you listening, that is the equivalent of several thousand residential homes running full tilt.
Like AC blasting,
Oh,
ovens on.
lights blazing,
Yeah.
everything, just to crunch numbers.
That is a massive energy bill. And well, that brings us to the core of today's deep dive. We've got a stack of research here focusing specifically on the work of Kevin Osborn at the Joint Quantum Institute in the University of Maryland. And the central thesis we're looking at is, it's terrifyingly simple, really. We are hitting a wall.
We are. We call it the exascale barrier. We've reached this point where computers are performing 10 to the power of 21 operations.
Which is an astronomical number.
It is, but the energy cost to get there is becoming completely unsustainable. It feels like we are trying to run a marathon while, wearing a backpack full of lead.
And the culprit here is the traditional silicon chip, right?
Yeah.
The CMOS technology that's been powering everything from our toasters to our Teslas for decades now.
Exactly. We have relied on CMOS, that's complementary metal oxide semiconductor, for 50 years. But we're hitting an efficiency wall.
Right.
You can only shrink transistors down so much before the physics just starts to fight you. The heat becomes unmanageable. But Osborn's team asked a great question. What if the problem isn't just the size of the switch?
Okay.
What if the problem is the fundamental physics of how we compute?
And that's the mission we are unpacking today. Because Osborn and his team, they aren't just trying to make a slightly better silicon chip. They're exploring a completely different path, something called ballistic computing.
Ballistic is the key word there. It implies a projectile, a trajectory.
It sounds like we are firing data out of a cannon.
In a way, we are, but instead of cannonballs, we are using something called fluxons. And instead of gunpowder, we're using the principles of reversible thermodynamics to sort of cheat, or rather, to avoid the energy bill that traditional computers have to pay.
Okay, before we get lost in the jargon, I need to make a massive clarification because I know you listeners are savvy. We are going to be talking about superconductors today.
Yes.
And we are going to use the word quantum quite a bit. But this is not quantum computing, right? We aren't talking about qubits and superposition and breaking encryption codes.
I'm so glad you brought that up early. It's a really important distinction. No, this is not quantum computing in the sense of Shor's algorithm or probabilistic answers.
Okay, good.
This is reversible digital computing. It uses the unique properties of quantum materials, specifically superconductors, to perform standard logic, zeros and ones, true and false.
So it solves the same exact problems my laptop solves, just differently.
Exactly. It solves them with an efficiency that standard chips basically can't even dream of. We are talking about getting within a factor of 100 of the fundamental quantum limit of energy efficiency.
Which is insane. So to understand why that efficiency is such a big deal and why silicon can't touch it, we have to talk about trash.
Trash.
Or rather, the trash can of logic. You brought up this concept earlier in our notes called the physics of forgetting.
Right. This goes back to the absolute basics of thermodynamics. There was a physicist named Rolf Landauer who formulated what we now call Landauer's principle.
Okay.
Simply put, it says that information is physical. It's not just abstract math floating in the ether. And when you erase a bit of information, when you forget it, you must dissipate a tiny amount of energy as heat.
Why does erasing create heat, though? That always feels counterintuitive to me. I feel like writing something down should take energy, but erasing it should just be free.
Think about entropy. Think about a messy room. If you want to clean it up, organize it, reset it to a blank slate, you have to expend energy, right?
Yeah, you generate body heat moving things around.
Exactly. In a computer logic gate, standard gates are what we call irreversible. So if you have an A and C gate and the output is 0, you don't know what the inputs were. They could have been 0 and 1 or 1 and 0 or 0 and 0.
You've lost that history.
You've forgotten the input. And that loss of history, that erasure, is what generates the heat. It dissipates an amount of energy defined mathematically as Boltzmann's constant times temperature times the natural log of 2.
Which sounds tiny.
It is. It's a tiny, tiny number. But when you are doing trillions of operations a second, it adds up to those 20 megawatts we talked about in the intro.
It's like wiping a chalkboard. The information is gone, But the chalk dust, the heat is released into the air.
That is a brilliant way to picture it, yes.
So if erasing is the problem, how does Kevin Osborn's team get around it?
They just stop erasing. Yeah, they use reversible computing. The idea was pioneered, theoretically, by Charlie Bennett at IBM decades ago. The concept is that if you don't erase the history of the computation, you simply don't have to pay that heat penalty.
Walk me through that. How do you compute without erasing anything?
You build a system that can run backwards, you compute forward to get your answer, you record the result, and then you effectively uncompute backward to return to the initial state.
Oh, wow.
By unwinding the process, you recover the energy you put in rather than dissipating it out as heat.
It's like regenerative braking in an electric car, but for logic.
That is a perfect analogy.
Okay.
In traditional CMOS chips, we measure energy cost in femtojoules. In this superconducting logic, we are talking about zeptojoules.
Which is orders of magnitude smaller.
It is incredibly more efficient because you aren't fighting electrical resistance, you are conserving momentum.
Okay, so we have the theory down. Don't erase, recycle the energy. Now let's meet the thing that actually does the work. The fluxon.
Right.
It sounds like a particle from Star Trek or something. What exactly is a fluxon?
A fluxon is a magnetic flux quantum. In the quantum world, magnetic fields are quantized, meaning they come in discrete little packets. A fluxon is one of those packets.
Got it.
But you can't just have this thing floating in the air. It's trapped inside a specific structure called a Long Josephson Junction, or LJJ.
And based on the source material here, this structure is basically a sandwich.
A tri-layer sandwich, yes. You have a base electrode made of niobium, that's your superconductor, then an incredibly thin barrier of aluminum oxide in the middle, and then a counter-electrode of niobium on top.
So a metal oxide metal sandwich.
Right, and this structure allows a quantum phase to wind around the barrier.
So the fluxon isn't a solid ball of matter. It's not a physical marble.
No, it's a soliton. It's a self-reinforcing wave packet that maintains its shape as it moves. But here is the kicker. Even though it's technically a wave, it acts remarkably like a particle.
The sources use the billiard ball model to explain this, which I found super helpful.
It is the best way to visualize it. Back in the 1980s, theorists imagined ballistic computers where data packets would just collide like billiard balls on a table.
Right.
If ball A hits ball B, they bounce off in totally predictable paths. No motors, no electricity pushing them along, just pure momentum conservation.
And Osborn's team is actually building that.
Taking that theoretical model and building it physically using these fluxons.
But here is where it gets really sci-fi, and I love this part. These fluxons have a speed limit, right? And that speed limit dictates their mass.
Yes. This is where we get relativity on a chip. Inside that Long Josephson junction, electromagnetic waves have a speed limit called the sweetheart velocity.
Sweetheart velocity.
Right. It's lower than the speed of light in a vacuum, about roughly 1/30th or so, depending on the materials. But for the fluxon, it acts exactly like the speed of light does in Einstein's relativity.
So as far as the fluxon is concerned, the sweetheart velocity is the cosmic speed limit. It is c.
Exactly. The fluxon has a rest mass, and as it speeds up and gets closer to that sweetheart velocity, its energy scales mathematically just like special relativity. It gets heavier.
That is wild.
The gamma factor, which anyone who's studied physics will recognize, starts to shoot up.
Usually when we design chips, we worry about voltage drops and resistance. Here, Osborn actually has to calculate the relativistic mass of his data bits.
It changes everything about the design. In standard electronics, you need constant voltage to push electrons against resistance. Here, because of that mass and the superconducting environment, the data actually has momentum.
You give the fluxon a kick, and it glides.
It coasts.
So we have our relativistic billiard balls. Now we need a table for them to play on. This brings us to the core innovation described in the research, the ballistic flip-flop, or as I like to call it, the BFF.
The BFF is the heart of this new architecture. It uses pairs of those Long Josephson junctions. But unlike traditional electronics that just use on or off, high voltage or low voltage, the BFF uses signal polarity.
This is the matter and antimatter part of the analogy.
Yeah, metaphorically, yeah. They use fluxons, which we can call positive, and anti-fluxons, which are negative. An anti-fluxon is really just a fluxon with the magnetic field pointing the opposite way.
So how does the gate actually work? How do you perform a calculation with that?
Think of the gate as a shift register or a storage loop. Let's say you have a bit stored in the loop. Maybe it's an anti-fluxon. When a new input fluxon arrives, it carries that relativistic momentum we talked about.
It's coming in hot.
Right. It smacks into the stored bit, kicks it out, and takes its place.
So the input becomes the memory, and the old memory gets knocked out to become the output.
Exactly. It's pure conservation of momentum. And because it relies on this collision rather than switching a transistor on and off with voltage, it's incredibly efficient. Simulations show this gate is over 97% efficient.
Where does the other 3% go?
The only energy lost is to tiny ripples in the superconductor called plasma waves, which are basically just sound waves in the electron sea.
There's another massive difference here regarding time. Most standard chips have a clock, right? Like a metronome. Tick-tock, everybody's step.
Right. Standard chips are synchronous. A global clock dictates exactly when every gate opens and closes. If a bit of data arrives early, it has to sit there and wait for the next tick.
And that waiting burns power.
It generates heat.
It's like a marching band. Everyone has to exactly in step.
Exactly.
Yeah.
And if one person stumbles, the whole formation messes up. The ballistic flip-flop, though, is asynchronous. It doesn't need a clock at all.
So it's more like highway traffic.
Even better. It's like a perfectly choreographed dance where the dancers just react to each other naturally. The bits arrive, do their momentum exchange, and leave. It's a flow of logic rather than a march.
Which increases speed and reduces power consumption.
Significantly.
Now, reading through the transcript from the USC Discover Expedition video, which, by the way, was a great look behind the scenes, it's clear this wasn't all smooth sailing. Theory is one thing, but building this physically, they hit a wall. They call it the splitting fluxons problem.
Yes, this is the classic theory meets reality moment. So they built this experimental setup. And first, they had to upgrade their cooling. They moved from a standard liquid helium container, a Duor, to a cryomic dry refrigerator.
Why the switch? Just to get it colder.
To get it quieter, actually. The dry fridge turned out to be better for reducing noise, which allows them to detect the precise timing of these tiny particles. They built a two-polarity detector to sort the positive fluxons from the negative anti-fluxons.
Because they needed to prove that both types could move ballistically.
Right.
And then the anti-fluxons started acting up.
They were misbehaving. When an anti-fluxon moved across the circuit, it had to cross these connections to the ground plane. Now, for you listening, a ground plane in a regular chip is usually just a stable reference point.
Nothing special.
But in a superconductor, you have the Meissner effect. Superconductors hate magnetic fields. They try to expel them.
So the chip is actively fighting the data moving through it.
Aggressively fighting it. In this specific early design, as the anti-fluxon crossed the ground lines, the superconductor created screening currents to compensate for that magnetic flux.
What does that actually do to the flux?
It grabs it. That screening current effectively trapped a ghost flux quantum in field, a parasitic bit of magnetic field between the ground and the junction.
That's like getting gum on your shoe while you're trying to sprint.
Exactly. It created drag. They realized that to push the data through this ghost, they needed a much higher bias current. They had to crank it up to 125 microamps instead of the expected 95.
Which defeats the entire purpose.
Yeah.
If you have to shove the data that hard, you aren't saving energy anymore. You're just burning it in a different way.
Correct. It completely broke the efficiency model. It looked like a failure.
So how do they fix it?
They realized the problem was the connection itself. They had a direct wire connection injecting the current. That physical connection was creating the ground loops. So Osborn's team totally redesigned the launcher. They switched to an inductively coupled launcher.
Inductively coupled, meaning they used magnets.
Magnetic fields, yes. Instead of touching the circuit with a wire, they use a magnetic field to push the fluxon into the system across a gap. No wire contact means no ground loop path.
And that solved it.
It eliminated the ghost flux, removed the drag, and brought the efficiency right back in line with their theoretical models.
It's fascinating how physical this all is.
Yeah.
We usually think of coding and logic as abstract math, but here, the actual geometry of the wires, how they cross, how they connect, determines whether the logic works or just gets stuck in a magnetic trap.
That is the reality of superconducting electronics. You are building a physical highway for quantum particles. The geometry is the logic. You can't just code your way out of a bad layout.
Speaking of layout, let's talk about the design reality.
Yeah.
They aren't just simulating this on a computer anymore. They're laying it out for actual fabrication.
Right. They are working with MIT Lincoln Labs, which is really one of the premier places for this kind of work in the world. They have a specialized process for niobium fabrication. We are talking about junctions that are incredibly powerful for their size current densities of 4 microamps per square micron.
And how big is this ballistic flip-flop? because supercomputers themselves are huge buildings.
The computer is huge, but the gates are microscopic. The critical interface in the BFF is only about 28 microns on a side.
Give me some context for that.
Well, a human hair is about 70 to 100 microns thick. So this entire logic gate, which handles relativistic collisions of magnetic particles, sits comfortably within the width of a single human hair.
I want to zoom out for a second and compare this to the competition. The source notes mention other superconducting attempts, things like RSFQ, rapid single flux quantum.
Yes.
Why hasn't that taken over the world yet? Why is Osborn's ballistic approach fundamentally different?
It really comes down to how you deliver power. Most other superconducting logic families, like RSFQ, are powered by rails. You have a DC or AC power source constantly feeding energy into the system to drive the switching.
So it's like a conveyor belt that's always running.
Exactly. Even if there are no boxes on the belt, the motor is spinning. It consumes power just to stay on. Osborn's reversible fluxon logic is entirely different. It is powered by the kinetic energy of the data itself.
Wait, unpack that. The data powers the chip.
Yes. Once you launch that fluxon, it glides. It has momentum. You don't need a power rail running into the gate to make the switch happen. The collision is the power source.
Wow.
The momentum of the input drives the output.
That is a massive shift in architecture.
It is. And that is exactly why it can reach that zeptojoule efficiency. It only uses energy when it is actually moving data.
So if we can pull this off, and I know FKV is doing a lot of heavy lifting there, but if we can scale this up from a single flip-flop to a full processor, what does the future look like?
We go right back to that 30 megawatt problem from the intro. If we can break the exascale barrier with this technology, we completely remove the energy constraint on computing power.
Because right now, we can build smarter computers, but we can't afford the electric bill.
Exactly. With ballistic reversible computing, we could theoretically increase processing power by orders of magnitude without needing a dedicated power plant for every single data center.
And it changes the speed, too. The readout times on these things are sub-nanosecond.
Yes, the bandwidth is enormous. And there's another huge benefit, heat density. Because it handles heat so differently, because it recycles energy, you could pack these processors much denser than silicon chips.
Because silicon melts if you stack it too tightly.
Right. But these run cold. You could build true 3D cubes of processing power.
It really feels like we are looking at the transistor moment for the 21st century. Silicon had a great run. It gave us the internet and smartphones. But the physics just don't scale anymore.
Silicon is hitting the wall of thermodynamics. Ballistic fluxons are trying to tunnel right through it. We are effectively moving from the electronics age to the fluxonics age.
Fluxonics, I like that. So to recap for you listening, we have a computing architecture that runs at relativistic speeds, uses matter and antimatter analogies on a chip, and recycles its own energy by running backwards to uncompute its own history.
A reversible motion machine, if you will. But yes, it is a completely new paradigm.
Here's a thought I want to leave you with, and I really want to hear your take on this too. We always talk about computers processing data. We treat data like raw material, like lumber that sits there, passive, while the saw works on it.
Right.
But in Kevin Osborn's model, the data is the process. The fluxon isn't just the number one. It's the thing doing the work, moving, colliding, and conserving its own momentum.
That's a profound shift in perspective. It blurs the line between the software and the hardware. The information is the energy.
If computers stop generating heat, if the act of thinking no longer costs energy in the way we've always understood it, does the limit on how smart our machines can get simply vanish?
That is the trillion-dollar question, and looking at this research, the answer might just be yes.
Something for you to think about while you plug in your phone tonight and feel that little brick get warm. Thanks for listening to this deep dive into the fluxon frontier.
It was a pleasure.
Catch you on the next one.